My name is Sami Al-Shal. I'm a professor of chemistry at Virginia Commonwealth University, and I'm conducting an interview with my colleague and my friend, John Fenn. Today we'll chat about his journey through vacuum and through mass spectrometry and molecular beam.
And 12th grade, and when I finished the 12th grade, I was only 15.
Oh.
And my mother and father thought it was too soon for me to go to college. I mean, I wasn't ready to go to college. So I stayed on an extra year. I was at Berea and took piano lessons and a course in mechanical drawing.
Oh, very nice.
And spent that year and had a chance to do a lot of reading and that sort of thing. And then I went on and finished college. I applied for admission at several universities, and I got admitted at Yale and at Northwestern University. Northwestern had a better chemistry department. I had a wonderful chemistry teacher at Berea, so I majored in chemistry. And Northwestern had reputedly a better chemistry department than Yale did. And he said, you go to Yale. He said, you'll be on the circuit. I said, well, they're not paying as much money. He says, that's irrelevant.
So you ended up at...
But it happened that the treasurer of Berea had a son who had been admitted to Yale as a freshman. And so he was going to drive his son up from Berea in the middle of Kentucky and install him as a freshman at Yale. And he offered me a free ride from the middle of Kentucky up to New Haven. And so I took advantage of that and got up to New Haven, and that's how I went to Yale instead of Northwestern. But there's an interesting one, it makes you wonder if there is a Nobel virus. Because I was in the physical chemistry group at Yale.
Right.
And while I was there, Lars Onsager got the Nobel Prize. Gus Akerlof's son went and did a graduate work in economics at in the University of California, I think it was. He got the Nobel Prize.
His son.
Yeah, and another guy by the name of Ray Davis got the Nobel Prize in physics. And so within a group, within a 5-year period, there were four Nobel Prizes that came out of Yale in the chemistry department.
Right. Did you ever take classes with Onsager?
Oh, yes. They were known as Norwegian 1 and Norwegian 2, beginning statistical mechanics and advanced statistical mechanics. Well, Lars was hopelessly brilliant. All you have to say is, I don't see, Dr. Onsager, how you got from this step to that step. And with that, he'd pick up a piece of chalk and he'd start on one end of, and I've seen him go right around the room, deriving anything right from scratch.
Amazing.
And there was not a mean bone in his body, but people would not come and give seminars at Yale because they'd start out and Onsager would raise a question. I said, I don't quite understand this. And Onsager would get up and take the chalk away from the speaker and derive it right there on the board. He was so brilliant that it was embarrassing.
Yeah.
Jim's job at Bell Labs,
yes.
He got attached to a group that was given the project of developing telemetering communication for this Project Bumblebee, which was going to be a ramjet-powered anti-aircraft missile. Right. According to all the laws of modern aerodynamics, it's impossible for a bumblebee to fly. But the bumblebee doesn't know any aerodynamics, so it goes ahead and flies anyway. And it was a big question mark. The U.S. had found out that the Germans were working on a ramjet thing.
I see.
And they had already made a lot of havoc with their pulse jets, you know. And so the U.S. was very susceptible to what the Germans might be doing. And so they started this ramjet-powered project under the auspices of the Navy. And they would boost them up with rockets.
Right.
And then when they got up to speed, the rockets would drop off, and they were supposed to start. Yeah. And every time they would start these things up and turn on the fire, the flame would blow out. And Jim watched this for a while, and he remembered his freshman chemistry. They were using kerosene as a fuel.
I see.
And he remembered that carbon bisulfide burned much more easily than hydrocarbons did.
Yes, sure.
So he was down there with this crew, and he said, why don't you try carbon bisulfide? Well, they were desperate. So they did. And they had a prune juice bottle, and he's got it. We've somewhere around home and home. We got the original prune juice bottle that they used. It was a prune juice bottle that came up like this and had a long spout on it, and they used that to pour the carbon bisulfide into this fuel tank of this test vehicle. And that the first flight test, when they used carbon bisulfide as a fuel, the fire burned and they got net thrust. And I moved to Richmond and started work at Experiment Incorporated. And Jim was a great believer in publishing results, and so we published a number of papers on stabilizing flames in high-speed flows. They had to find somebody to be director of this Navy project Squid. And so somebody put my name in the pot, and they offered me a job. I was down in Richmond at the time, but they offered me a job, and Richmond was a hotbed of Princeton graduates. Jim himself was a Princeton man, and all his friends in Richmond were Princeton graduates. And so I was brainwashed with how wonderful Princeton was.
Of course, yeah.
And so when the chance came to go to Princeton and run this research program for the Navy, and I had pretty good connections to the Navy, well, I thought it looked too good, so I went.
Of course you took it, yes, yes.
And the first thing the Navy did was, after I got there, was to put me in London. Our children, my 3 kids, will tell you to this day that those 2 years in London were the high point in the Fenn family fortunes. Everything's been downhill since then. It was a wonderful year. Yale had seen the success of this Project Squid, and so they decided they wanted to do something like that. And so they offered me a job and they were starting up an aeronautical engineering group, and they offered me a job up at Yale. Flame theory was the hot thing. I mean, what determines the propagation rate and all that stuff. And von Karman and Hirschfelder were 2 different schools of thought on flame propagation. Joe Hirschfelder was a physical chemist.
Right.
And so it was H-atom migration which was determining everything. Yes. And von Karman was of a bit of a different cut. He was much more practical. He was an engineer. He was a remarkable man. And so they had, I can remember going to combustion symposium meetings, and there was the von Karman group on one side on the big argument, what was the propagation mechanism for flames, and hydrogen diffusion or thermal conductivity or what. And so, boy, there used to be knockdown, drag-out blows between the Hirschfelder group and the von Karman group. And I'll never forget one when they had this Agard symposium in London, and I went to it. And the 2 groups, von Karman got up and gave his latest spiel on flame propagation. And it was based on, and a key component of it was the diffusion velocity of hydrogen atoms. And so in the question period, somebody asked von Karman, what were they using as the diffusion coefficient for hydrogen atoms? Well, he didn't know what they got. So he asked one of his colleagues who was there. The Hirschfelder group was over here, and you know Joe Hirschfelder.
Yes, yes.
He's very excitable and whatnot. And so von Karman finally turned to his colleague and said, where do we get the hydrogen atom diffusivity factors? And this guy said, well, we got them from Hirschfelder. And so with that, Joe Hirschfelder jumped to his feet and says, you see, they even copy our mistakes. Because the number that they'd copied out of the literature from this was wrong. I had been fascinated by molecular beam experiments. You know the wonderful story about the Stern-Gerlach experiment. Gerlach, who was Stern's assistant, when they did this experiment, and they ran it, and when they took out the glass plate that they caught the plates on, there was no deposit. Nothing. Oh. Gerlach came to Stern and said, I'm sorry, Herr Professor, Dr. Sir, and clicked his heels, I'm sure, because the Germans are very... the experiment was a failure.
It didn't work,
we don't get any... And so Stern picks up this glass plate. Sure enough, there's nothing on it. But while he's looking at it, these 2 lines appear.
Wow.
Well, it turns out Stern was a heavy smoker. He loved to smoke. He could only afford cheap cigarettes, and they had lots of sulfur in them. And so this silver pattern had been deposited but wasn't visible. But when Stern looked at the glass plate, the cigarette smoke deposited the sulfur on there, and so these two lines of silver sulfide appeared.
I see.
And Stern used to love to say after that he got the Nobel Prize for that experiment, because it was to prove the Bohr atom theory of
right. The split.
and he got the Nobel Prize because he smoked cheap cigars. I figured that beams were really the way to look at chemical kinetics. Well, we had already been doing some free jet expansions, and we knew from our molecular beam work that we could get heavy molecules up to the speed of the hydrogen molecules by the seeding process. And so when you do a few calculations, you suddenly realize you can get heavy atoms up into several eV of energy with no problem at all, and plenty of intensity. And so I put in a proposal to the Navy, through Project Squid, to get some vacuum pumps so that we could use these free jet expansions to produce beams which have kinetic energies of several eV. I put in this proposal, and lo and behold, Esterman, who was in the molecular beam business, was one of Stern's colleagues. And lo and behold, he came up to visit our lab to discuss this proposal. And so he gave us the money with which we bought these huge vacuum pumps. And one thing that we had learned from the beam business is that you never had enough pumping speed. And we started out making supersonic free jet expansion and taking the core out to make beams, and we were getting beams with any energy we wanted to, and we were doing scattering experiments off surfaces and whatnot that nobody had ever dreamed about doing before. And so we began to get people would come. They would come and take one look at these big 32-inch diameter diffusion pumps and say, well, that's very nice, but not for us. And so we scared off the competition. We had the whole field to ourselves for several years there. We wanted to get bigger molecules. And so one way of getting bigger molecules is to take a solution and disperse it and let the solvent evaporate. And we were going to make, we knew we could get ions this way, and we would then neutralize the ions. And so we looked at, the first experiment we did was the sticking coefficient for silver on silver atoms on a glass surface. Because we could make the beam of silver atoms and vary the energy all over the place and see what the sticking probability was. And then we learned that you could look at the velocity distribution of these things, and you could learn things about the rotational, vibrational transitions and the probabilities of them. And so we learned lots of things about the vibrational relaxation rates in gases, how fast your vibration could turn into translation. And people got very interested. We'd get these, every compound gave rise to a spectrum which had 10 peaks in it.
Right, because it's a multiple charge.
And everybody said, well, that's hopeless. I mean, you never can figure out anything what's going on. I remember walking into the lab one day with one of these spectra, and I say, you know, if you stop to think about it, each one of these peaks is the same molecule, the only difference is the number of charges. And so each one of them, in principle, is a measure, an independent measure of the mass of the parent molecule. There ought to be some way that we can average those values. And I came back 2 days later, Jim Anderson had worked out the algorithm by which you could, taking advantage of the fact that the difference between the ions of one peak and an adjacent peak was simply one charge. My latest thing that is some experiments I did quite some time ago now, but I want to go back and look at them, and that's bringing about what I call the condensation laser. How does a laser work? You remove the ground state, right? When you do these free jet expansions, you condense out the ground state. And so that means that there's nothing to soak up the electrons, and so they are emitted. And so I know, just as sure as I'm sitting here, that we can build lasers which have tremendous output, because you can get thousands of these small jets, each one of them in a small cross-sectional area, putting out photons to beat the band. This Frida woke me up and said, honey, the telephone. It was about 6:30 in the morning, something like that. And so I answered, and I said hello, and they said, this is so-and-so from Stockholm calling, and we wanted you to know we've just released to the press the names of the people that are going to share the Nobel Prize this year, and you are sharing the Nobel Prize in chemistry. And so you can expect your telephone to start ringing in about half an hour. That's what they told me. I went to Stockholm and had a heart attack. And of course, they handled you with velvet gloves over there, where you have a limousine and a personal limousine with this keeper that takes you everywhere. But she was the one that, when I just happened to mention it, and I didn't feel bad. I wasn't feeling badly at all. I just noticed I felt a little dizzy or something up there.
Dizzy, I see.
And so, next thing I knew, I was in the hospital.
And so then you became much younger.
No, I became older, but no wiser yet. Dudley Hirschbach's going to be here. He's coming to visit somebody at the University of Richmond on Monday.
Yes.
But Dudley, he's one of my favorite people. Dudley's the guy, you know the little book I wrote on thermodynamics? I had written up this manuscript, and Dudley, he writes poems sometimes.
Right.
And so I had this manuscript up that I'd written up on this book, Possibility, and Dudley sent me a copy of his latest book on a poem, poem on a particular flower, I think it was. So I sent Dudley a box. I said, you send me
poems,
a one-page poem, I'm sending you a 50-page manuscript. Well, it happened that the guy from the West Coast printer had come to see Dudley about the possibility of his doing a book for them. And he'd just gotten this thing, and it apparently struck his fancy, but he said to the chap, he says, no, I've already done my first job for you. You got to publish this book. And so he gave him this manuscript that I put together on engines, energy, and entropy. I think it's a damn good introduction to thermodynamics. It ought to be the textbook for the first course in thermodynamics.
Right.
Because none of these others ever tell you what a property is, for example.
Yes.
But the thing is, the thing that bothers me about courses ought to be fun.
Yeah. Well,
but they're all emphasis. You got to cover everything.
Yeah.
Hey, that's not important. The thing that what a course should do is get a student interested. I would never major in chemistry if I was starting today. The whole thing is they got to cover everything. That's a lot of baloney. And there's no fun anymore in it. And look at the chemistry books. They get thicker and thicker and thicker. There's a fundamental fallacy that in chemistry, for example, we know more chemistry today than we did 50 years ago, so the students have to learn more today than they did 50 years ago. But that overlooks the fact that the student's brain today is the same as it was 50 years ago and the same as it'll be 50 years from now. Just because more is known doesn't mean that the student has to learn more. The student ought to learn how to use his brain. Education is not training. It's developing young people's minds.
Thank you very much, John.
I'm always glad to preach when I can get somebody to listen.